Okay, let's go through a redo of the hats lecture, this time with both sound and the slides. Again, I'm sorry for the issues we've had before. Okay, so here's a classic problem. You and 9 of your closest friends are shipwrecked, as happens, on a tropical island. Why should it be a desert island? There's a human-eating monster there. I'm going to call him Fenrir, who's a giant wolf in Norse mythology who will eat Odin at Ragnarok and then be avenged by Vidar. But anyway, different monster, same name. And Fenrir wants to eat you, but you beg for mercy, and Fenrir, being a puppy of good taste, agrees to give you a sporting chance. He'll come back tomorrow, line you up, he'll put a black and white hat on each head, and ask you from the back, what's your hat color? Do you have a black one or a white one? He loves puzzles. Anyway, so he'll ask the guy at the back, what color's your hat? This guy can see everyone in front of him, and he'll either say black or white. Everyone can hear this, but can't necessarily they don't know if he's right or not. Then he talks to the second guy, hey, what color is your hat? It says black or white. Everyone can hear this, and he'll be eaten if it's wrong, and left off the island if it's right. Okay, so so everyone's trying to get their own hair color right, and they're also trying to pass information forward. Okay, and you've got the knight, so you think, hey guys, maybe we can come up with a code and save some of us. Okay, so 10's a bit big, but let's try some smaller cases. So 2 people. The guy at the back will just tell the guy at the front, hey, it's a black hat. If it's black, or he'll say black or white. Well, he can't just tell him, but he'll say beforehand, look, I'll say the color of your hat, you'll just copy it. Okay, the 3-person case is usually where people get stuck with this. They say, oh, well, the back guy will tell the second guy, and the second guy will just tell the third guy. Well, the point where that breaks down is if 2 and 3 have different hats, the middle guy is now forced to choose between saving himself and saving the guy at the front. And the workaround here is for the guy at the back to say black if they're the same and white if they're different. Okay, then the middle guy, he knows if he's the same color as the guy in front of him. He can see the guy in front of him. And so he'll say his hat color. The guy at the front knows if he's the same as the middle guy. And he might as well be able to see his hat color because he knows that this guy's in the middle is going to get it right. And so he can also get it right. Now, fourth word gets tricky. But it's the last place you need a new idea. And in this case, the guy at the back is just going to say, if I see an odd number of white hats, I'll say white. If I see an even number of white hats, I'll say black. Okay, second guy can see everyone in front of him. He knows if, including his own hat, there's an even or odd number of white hats. And he'll just say, well, okay, I can work out from that if I've got a black or white hat. Third guy might as well be able to see the second guy because he knows the second guy got it right. Everyone in front of him he can see. He knows what the total number of hats is. He can work things out, and he gets it right. Fourth guy might as well be able to see 2 and 3 because he heard them. He knows they were right. He can see everyone in front. He knows what the total number of black and white hats are, or if it's even or odd, and he can work out his own, and so on. And this works for 4, 5, 6, as many people as you like. you can save everyone but possibly the back guy who's a 50-50. Okay, so harder version. Fenrir lets you off the island, but you meet a bigger monster, his little brother Jomungard, a giant serpent who kills off Thor and gets killed off at the same time in Ragnarok, or will, depending on how you want to treat this. And Jormungand wants to play this game too, but instead of just having black and white hats, he's got hats of, well, let's say K colors, because there are N people. Okay, this fabulous array of many colored hats, white and red and yellow, black, etc. What do? Well, the answer turns out to be modular arithmetic. You call one color 0, one color 1, one color 2, 3, 4, 5, up to k minus 1. The guy at the back adds everything up and just says what the checks and says what the sum of everyone's hats is mod k. Now this is nice. The second guy sees everyone else's hats. He knows what they are mod k. He can work out what he needs to add to get to the right value mod k. He adds up everyone's hats. He does that. He gets it right. Everyone else might as well be able to see him because he just got it right. So everyone else can also do this trick in exactly the same way. If you're the fifth guy, you've heard what 2, 3, and 4 have. You can see what 6, 7, 8, 9, 10 have. You know what the total checksum is. You work out what everyone else's stuff adds up to. You know it's meant to be a 3. It is a 7, and you're working mod 8. Okay, your hat color has to be 4. You say 4 and you win. So that's quite nice. Okay, so here's a slightly harder version. You get to the third monster. Hell. Yep, like from Thor. And again, Fenrir, Jormungand, and Hel are the 3 children of Loki, with giantess whose name I can't remember. But, okay, so we finally get onto the third island, Hel. And she's somehow a lot of people have joined you. You've now got countably many people. Countably infinite many people. All in a really long line, and Hel's like, okay, cool, fine, you can save all but one with my brothers, but with me you have to save all but finitely many. Okay, and 2 hat colors doesn't make the problem any easier or harder. Okay, so the first thing you do is you say, look, we're going to get a sequence of zeros and ones, or a sequence of numbers, and we're going to talk about 2 sequences as equivalent if they are eventually the same. Okay, among all possibilities of hats. Now, to be equivalence classes, you need a few things. First, you need everything to be in the same equivalence class as itself, but a sequence of hats and another sequence of hats a sequence of hats and the same sequence of hats are eventually the same. They're the same from step 1. Then you need that if I'm eventually the same as you, you're eventually the same as me. Well, that's true. And then you need if A is equivalent to B and B is equivalent to C, that A is also equivalent to C. But we have this too. Okay, so we divide up sequences of hats according to if they're eventually the same. And by the axiom of choice, we can choose from each of these classes a single representative. Okay, that's the axiom of choice step. And you're only going to be wrong for finitely many hats. Possibly infinitely many on average, but finitely many for every particular run. There are ways of getting this. So if I'm going to get 2 rand with probability a half, and 4 rand with probability a quarter, and 8 rand with probability an eighth, and 16 rand with probability a 16th, and 32 rand with probability a 1 out of 32. and I want to, and so on. I want to add this up. You get 1 plus 1 plus 1, and this goes off to infinity. So that is actually a thing that can happen. Okay. But yeah, it turns out you can actually get out of Hell's problem. So, circle game. 10 of you finally get off the island. But you are immediately arrested, not asserted, for something. And, you know, in this world, police officers, much like Norse mythological monsters, love puzzles. I mean, doesn't everyone love puzzles? Okay, so they're going to put black, white hats on each of your heads, and you're all going to vote on your own hat color. You're also going to vote with a particular weight, and you can vote with weight 0, weight 1, weight 2, weight 3, weight a billion, weight 0.05, whatever you want. And you all win or all lose together, if and only if your total correct weighted guesses is better than your total incorrect weighted guesses. So if I say I've got a white hat, and my weight is 5, and it's a white hat, I get 5 points for all of us. But if you say black and 6, and you happen to have a white hat on also, you lose 6 points for us. We're going to add everyone together, and you get out if and only if, or we all get out if and only if we have a positive score. Sometimes this problem is phrased as a graduating mathematics class. And they pass or fail. I like these exams. Anyway. So, possibly everyone gets a black hat. You know, 8 of us, or 9 of us guess black and put weight 1. And the last guy guesses white with weight 1,000. We get 9 points minus 1,000. That's negative. And because of this one guy, we're all dead. Okay. Well, or convicted or something, right? Now, you're as likely to be right or wrong no matter what you do. You have no way to get any information about your own head. Okay, so the total score on average will be 0. Okay, if I add up everyone's score, it's going to average out to 0. There are 2 to the n colorings. So what I want to do, because we only care for positive or negative, is get, you know, slightly positive almost everywhere and like be really, really like minus a billion negative on the last one. Okay. Turns out you can do this. Player 1, let's say he's just going to guess white with weight 1. Everyone else can see if he got it right. So they're all just going to vote. If he's right, everyone just put down a 0. We're all walking out of here without degrees. Okay? If he's wrong, though, player 2 is like, well, gee, you know, I might have a white hat. I'm going to guess it with 2. If I'm right, my 2 will outweigh his 1, and we're done. If I'm wrong, well, we were wrong anyway, so it's fine. Now, player 3, and 4 and 5 and 6 and everyone, we can see player 2 and player 1. We know if between them they're going to get us out. If they are, guess 0. Cool, we're done. We're good. If, however, they're both going to get it wrong, player 3 can go, gee, well, he's getting a -1 and he's getting a -2. I'm going to bet 4. And I'll guess I've got a white hat, too. If I am right, and I actually have a white hat, well, my 4 is going to outweigh that -1 and -2, and we're all safe. On the other hand, if I'm wrong, well, we're on -7, and what do you do? Well, what happens then is player 4 jumps in with 8, and player 5, if he needs to, jumps in with 16, and so on. So the only way we lose here is if we all have a black hat. Okay. Now let's move on to a game where we have an infinite amount of hats each. Okay, hats 1, 2, 3, and 4. And 5 and 6 and 7. So, big stack of hats. Okay, they're randomly black or white. We can talk before the hats are on, but not after. And at the same time, we need to pick a hat on our own head. If we both pick white, we win, otherwise we lose. Can we do better than a quarter? Turns out yes. Okay, and the easiest way to do that is with a 1/3 strategy. So what you do is you say, look, I'm going to look at your hat, and the first white hat I see, I'm going to point to that one on my own head. You're going to do the same. You're going to point to the first white hat on my head. It's equivalent on your head. Now, maybe the first two hats are black. Well, we're just going to move up. Eventually, or maybe the second, maybe the 2 2s are black. Maybe the 2 3s are black. But eventually, we get to the first height on these stack of hats where one of us has a white hat. So either I've got a white one, you've got a black one, you've got a white one, I've got a black one, or we both have white hats. We're only going to win if we both have white hats. If we both have white hats, we'll point to them, we'll win. Okay? If not, I'm going to see your white hat, point to my black hat, or the other way around, and we're going to lose. Still, this gets us to win with probability a third, which is better than probability a quarter. Can you do any better? Yep. There's a 0.35 strategy. This strategy, me and quite a few other people found by computer search. What you do is you look at the first 3 hats, and if they're all the same color, you move up to 4, 5, 6 on the other guy's head. And this effectively lets you get rid of hats 1, 2, and 3. Oh, sorry. This lets you, of the 64 possibilities you could see with 3 hats, this lets you get rid of the 4 monochrome ones. So you have 3 black ones, I have 3 black ones is one, or I have 3 white and you have 3 whites is another one, or I have 3 black and you have 3 white, or you have 3 black and I have 3 white. So now there's 60 options, and you do an exhaustive computer search, you can find 21 of them working, and that gets you a 0.35 strategy. This is conjectured as optimal. Turns out there is an upper bound of 0.375 due to Nogolon. So what he said is, okay, I'm going to give you a little bit of extra information here. I'm going to tell player 1 what hat he's getting in advance. Well, I'm not going to be quite that nice. I'm going to tell him, look, you're either getting this set, or you're getting the opposite. So either all white, either this particular collection of black and white hats, or it's inverse. So if the first, either A or A prime. A is maybe white, black, white, blah, blah, blah. In that case, A prime is black, white, black. Okay, it's inverted. Okay, cool. What are your strategies now? Player 2, who's going to see either X or, well, either A or A prime. Well, you pick a hat on your head if it's A, and you pick a hat on your head if it's A prime. Or you pick the same hat. Either you pick the same hats or different hats. If you pick the same hat, you're going to do what you do. If 50-50, you win. This guy's going to look, he's not getting any information, he's going to 50-50, he's going to get 0.25. That's bad. Okay. But what if he picks 2 different ones? Well, if he gets black in both of those, we're dead anyway. But if he has a white hat, or if he's got 2 white hats, then it doesn't matter what the guy who knows he's got A or A prime does. He's got a 50-50 shot, and this is a 1/4 case, so that's an 1/8. It's also the case where he's got a white hat and the other guy, or this guy's got a white hat or a black hat. In that case, player 1 has a choice between A or A prime. He'll do the thing which matches the white hat. Best case, you might actually win there. That gets you also probability an eighth, and if it's flipped the other way, another eighth, so that's where you get 3/8 from. You can get slightly more, in order to get more precise upper bounds, you give him some smaller amount of information, and then you have to check, well, the other guy has to choose K hats, and possibly with some equivalence classes, and you get an upper bound. You can check all of those. They grow super exponentially, but you can check some slightly bigger ones and you get an upper bound of, I think, 0.3625. Okay, there's a little bit more work here. What if you've got 3 players, 4 players, 5 players, n players? We don't know too much. I'm told that you can get that as additional players are added, you always get strictly worse. There are strategies which are of order 1 over log n, which is surprising. You'd think it would be sort of, if you just play randomly, it's order 1 over 2 to the n. Possibly, maybe you think you could get like 1 over n, but actually it looks like you can get 1 over log n. And if you require, say, k out of n people to be right, well, there are 41 of you and 13 of you need to get it right to win. What happens, we don't know. And that is the talk on hats. Thanks.